So welcome to the second part of this lecture. We had just introduced the concept of head loss, which is due to friction. This is something that we need to be able to account for if we're going to come up with an accurate way to model discharge using an equation. And so to figure out how we deal with this, let's just kind of go through a graphical depiction of what's happening as you move from an upstream location to a downstream location within a river. So this brown color here represents the riverbed. So rivers slope downstream, and we could actually represent the elevation head of the bed. Let's just say our datum is somewhere down here. So this is z equals 0. So this is our zb at point 1. We'd have a much lower zb at point 2. So there's our elevation head component of the Bernoulli equation, and then we have a pressure head that's due to hydrostatic pressure. So hydrostatic pressure, remember, rho GH is determined by the depth of the river. So the second term in the Bernoulli equation, the pressure head, is equal to total pressure, or rho GH. So remember, P equals rho GH. But the second term of the Bernoulli equation is P over rho G, and so the rho G's cancel out, and what we end up with for this second term in the Bernoulli equation is just H. So we have our river depth upstream, our river depth downstream, and then even though it's not something we could see, we could actually draw a representation of the dynamic head or the velocity head. I'll just use a dashed line since this is not something we could see, but it is the third component of the Bernoulli equation. So this is u squared over 2g. We could draw it like this because it has the same units as water depth and elevation head. These are all units of length. So u squared over 2g. And then the total head at this point looks like it would decrease as you go from point 1 over here to point 2 down here. But we know that's not the case. Total head has to be conserved along streamlines, and so we actually need to add another term to account for the loss in head due to friction, and this is our head loss term. So this line here represents our total head, which is conserved from upstream to downstream, and the distance between the sum of the pressure head, the velocity head, and the elevation head, and the total head is equal to the head loss. Okay? So we could define a new term, which is friction slope, and friction slope is just defined as the slope that this angle here makes. So the slope is rise over run. So the friction slope is defined as head loss over the distance between 1 and 2, which I'm defining as L. Okay? So that's our friction slope. So now I'm going to rewrite the Bernoulli equation, or actually the change in the different terms of the Bernoulli equation in a somewhat different way. So because total head is conserved, we can say that the change in specific energy, remember specific energy is equal to h plus u squared over 2g. So the change in specific energy over change in longitudinal distance along the stream, plus the change in the bed height over that same distance, plus the friction slope has to equal 0. Okay? So this term that we have right here is just equal to the bed slope, which is often abbreviated in hydrology with a capital S. So therefore, the change in specific energy per length of stream is just equal to the bed slope minus the friction slope. This should be a minus S up here. Okay, now we can describe a special case. So if we have uniform flow, then the depth of the stream and the velocity of the stream don't change as you move from upstream to downstream. So in uniform flow, H and U don't change with distance. So delta E over delta X has to equal 0. And when delta E over delta X here equals 0, the bed slope has to equal the friction slope. So this is an assumption that's commonly made. So it's just commonly assumed that the friction slope is equal to the bed slope. Okay, so Darcy and Weisbach came up with a way to actually represent the friction slope in turbulent flow. And they came up with an equation for flow that includes a friction factor to represent the effects of head loss. So what they're assuming here is that the friction slope, which remember we defined earlier as the head loss over a length of interest, what they assumed is that this head loss should be proportional to a friction factor, so how much friction a given unit area of stream bed has. It should also be proportional to velocity squared, and this just comes from the fact that there is usually a squared relationship between drag or total friction and velocity. And they'll just divide this by 2g. And then there's another constant down here of 4. We won't get into the reasons for the 4. But there's another term in the denominator. So the friction slope is inversely proportional to the hydraulic radius. Now the hydraulic radius is defined as the cross-sectional area of the flow divided by the wetted perimeter. So because the wetted perimeter is in the denominator of the hydraulic radius, it would be in the numerator of this equation, and so therefore friction slope would increase with the wetted perimeter of the stream. So let's just go ahead and draw what these different quantities are. So let's assume we have a roughly rectangular channel. Here's our water surface. This is our channel depth, and this is our channel width. In this particular case, the hydraulic radius is just equal to the area, which is the width times the depth, divided by the wetted perimeter. So we have an H on the right side, we have an H on the left side. Our wetted perimeter then is just 2H plus W. Okay, for wide, shallow flow, the inequality of the width being much greater than the channel depth is satisfied, and we could approximate the hydraulic radius as approximately equal to WH over over W, because we're going to ignore those two H's, and we could say that the hydraulic radius is approximately equal to the channel depth. This ends up being a useful assumption a little bit later on. So the Darcy-Weisbach equation is one of the 3 equations that's commonly used to predict velocity within a channel and to predict discharge. However, there are some other equations that are even more commonly used. There's the Chasey equation and the Manning equation. Now, the Chasey modification is that, so if we were to solve Darcy-Weisbach's relationship, we would end up with U equals the square root of 8g times the friction slope, which is often approximated as the bed slope, assuming uniform conditions, times this area divided by the wetted perimeter, or the hydraulic radius divided by the friction factor. So Chasey simplified this and said that this whole thing was just equal to a Chasey friction factor. so a different friction factor, times the square root of S times the hydraulic radius. The problem with this, though, is that experiments revealed that this friction factor, this C in the equation, depended on both the bottom roughness and the hydraulic radius. And once people figured out that dependency, the Manning equation came to be, which separated out those two different influences. The Manning equation is probably the most common equation that's used to predict flow velocity and to predict discharge. Now, in the Manning equation, we have velocity is equal to, this is a K, over N, we'll get into what these terms are in a moment, times the hydraulic radius to the 2/3 power, times the bed slope, which is used to approximate the friction slope, to the 1/2 power. So K is a dimensional constant that's used to put everything into the right units. It's kind of a fudge factor. It is a nice term in SI, but it's a horrible term if we're dealing with English units. And this N here is the Manning coefficient, which is a dimensionless coefficient representative of roughness. So high values of N are surfaces that have very high levels of friction. Low values of N have levels of friction. So we could visualize this. So here are two different rivers. We have on the right a weed-choked stream with a Manning's N of 0.75. This is in metric units. And then we have the Salmon River in Idaho, which is a sandbed stream, has a much lower Manning's N and a much higher velocity. So there's high friction here due to the weeds, low friction here because the bed is relatively smooth and it's comprised of sand. You could convince yourself that these equations work out. Here we've assumed a bed slope of 6 times 10 to the minus 4, which is fairly reasonable, and a hydraulic radius of 3 meters. Now, one thing that we find in practice is that Manning's N isn't necessarily constant for a particular stream, but rather as the level of the water in that stream goes up, the relative influence of bed friction goes down, and so Manning's actually decreases with discharge, which is what you see on this plot. So as discharge increases, the value of Manning's N goes down. Now, the Manning equation makes a few assumptions. It assumes, first of all, that the flow is steady, that it is uniform. Remember, this uniform assumption gives us SF equals S. It also assumes that the flow is turbulent and that the friction is dominated by the bed rather than things sticking up from the bottom of the river, such as plants. The Manning's N values are usually determined empirically. There are actually tables in engineering textbooks that will let you know what the value of Manning's N is for a given stream. Okay, in this next section, we'll be talking about how we actually might measure discharge in the field. So remember in class on Thursday, we talked about critical, subcritical, and supercritical flow. Well, it turns out that we could put structures in streams. We could put artificial bumps in streams that induce a transition from subcritical flow, seen upstream here, to supercritical flow, seen downstream. So this is supercritical. At the bump itself, we have critical flow. So if we know we have critical flow, there's one particular solution to that specific energy equation, and we could actually apply the Bernoulli equation to solve for discharge based on the water depth just upstream of the weir, or the water depth that you could see in this particular profile. Your textbook goes into greater detail here. I'm not going to go into too much detail. This is not something that we will do in practice in this class. Some people consider this to be an invasive technique to measure discharge. It can be difficult, for instance, for fish to swim upstream over weirs. Probably not the small weir that you see here, but for a lot of other weirs, the passage of fish and other wildlife can be prohibitive. And so we tend to prefer less invasive ways of measuring discharge of streams. One of the more common ways to measure discharge is actually to divide up the cross-sectional area of the stream that you see here into a number of polygons, either rectangles or trapezoids. We'll use the trapezoidal method in this class. But then to actually measure a velocity that's representative of each one of these individual polygons, multiply that by the cross-sectional area to get discharge, keeping in mind that discharge equals area times velocity. So in other words, within this individual polygon, we would be measuring what's called an incremental area. So measure incremental discharge, which is just the Q flowing through that individual polygon. And then we could add up the discharge in each of these measured sections and say that our total discharge is equal to the sum of the incremental discharges. This is a concept that's fairly simple. It's based on geometry and the notion that discharge is equal to times velocity. So how might we do this in practice? Well, the most common method that we employ is the trapezoidal method. Remember, the area of a trapezoid is equal to 1/2 times this length 1. Wait, that didn't come out well. Let me rewrite that. So let's just use a cursive L. So length 1. And then this is length 2, so it's 1/2 of length 1 plus length 2 times the width of that trapezoid. So if we measure a velocity at this yellow point and assume that that is representative of the polygon, then we could say Q equals U at this point times the area of that trapezoid. And this is just an incremental Q. And then you add them all together for each of these different increments. So this is just showing how that equation would look when you do that over each one of the polygons within this stream. So in this particular diagram, we're measuring a mean velocity, which we just often assume is the velocity measured in the center of each one of these polygons. So Q here would be equal to this incremental area. So using the convention of the top equation, d0 plus d1 over 2 times width 1 times this measured velocity 1 plus and so on all the way to n. So dn minus 1 plus dn over 2 times wn times vn. Okay? Turns out, though, that this way of measuring discharge is a little bit cumbersome because it requires you to measure channel depth at each of these lines, but then measure velocity in the middle. In practice, it's a lot more convenient for us to measure depth at the same points along the stream where we're measuring velocity, and this is in fact in Strawberry Creek. So this is actually a much more common situation where we have, actually one that we just did, so I'm going to skip that one. This is a much more common situation where we have velocity and depth at each one of these solid lines depicted here. But the polygons that we're solving for are these areas in the middle, right here. Whoa, that is huge. Let's try that again. So these areas, okay? So how do we deal with that? Well, we could modify the equation somewhat, and we could say that the velocity that we're assuming to be representative of each one of those polygons is the average of the two velocities on the outside of the polygons. And so now the way that we would write this is, I have to change my pen size again. Okay, so now the way that we would write this would be Q equals, let's just do an incremental velocity between A and B. So we're talking about this polygon that I'm outlining in black. Okay. So the incremental discharge through A and B would be equal to just the average of the velocity measured at point A plus the velocity measured at point B times, here's where we apply the trapezoidal rule to calculate the incremental area. So dA plus dB over 2 times W. And so you would do this for each one of the polygons. Now you'll notice a few abbreviations here. You have LEW, which stands for left edge of the water, and REW, which stands for right edge of the water. This is looking downstream. And so generally we can't measure velocity right where the stream channel meets the bank, and so what we do is we apply the no-slip condition where velocity equals 0, and we also assume that depth, so this is at the right edge of the water, depth at the right edge of the water also equals 0. And then we could just apply this equation throughout to calculate each incremental area. So this is the equation for discharge. Through each incremental area. So the way we measure velocity within each one of these incremental areas is with a current meter. There's a few different types of current meters. Some of them have spinning cups. Some of them, the ones that have spinning cups typically make a click every time the cup goes around in a full rotation, and the observer would count the number of clicks. The one that you'll be using in Strawberry Creek is actually a little nicer. It's very high-tech. It's state-of-the-art, and it's called an acoustic Doppler velocimeter. I'll explain in person how it works, but it operates off of the principle of acoustic scattering off of particles within the water. I'm going to go through this fast because we'll talk about a lot of this in person. So the current meter is mounted on a rod, which is called a weighting rod. The weighting rod is a tool that you could use to measure depth and to set the height at which you measure velocity. Remember, you want to measure velocity 0.6 of the way down into the water column. Now the weighting rod is marked in increments of 10 centimeters. You have double markings every 20 centimeters, triple markings every 50 centimeters. This just makes it easier for you to stick it into the stream and be able to tell pretty rapidly what the water depth is. It's a very neat instrument because it's easy to set the flow meter to 0.6 of the way down the water column or 0.4 of the way up the water column. But if you're measuring a very deep stream, rather than getting that one velocity point, it's often considered more accurate to measure velocity at 0.2 of the water depth and 0.8 of the water depth. And it's also easy to set the weighting rod to measure that. So the top part of the weighting rod is called the vernier, and it is just a feature like what you see here that is marked with numbers. So once you measure the depth of the stream, you can match the number that's on the cylindrical rod up with a number that's on the vernier in order to set the depth of the instrument properly. This will make a lot more sense when we're actually out in the field. But as an example, let's say we measured a water depth of 42 centimeters. Now to set the height of the instrument properly, you would match the 4 on the cylindrical rod that you could see here up with the 2 that's actually on the vernier, and the instrument will automatically be set to the position. So if you were in a deep stream, which we won't be in Strawberry Creek, and you wanted to measure 0.2 of the way up from the stream bed and 0.8 of the way up from the stream bed, there's also a way to set those on the vernier, but we won't go over that in this class. Now there are some rules of thumb when making these discharge measurements. One is that you don't want to disturb the flow by your own presence in the stream, and so you want to stand downstream of the instrument and a little bit off to the side. In this particular case, flow is going from this end of the picture to this end of the picture. The other thing is that you'll see that the ADV that we're using has a red probe, and that should be pointing downstream. And again, we'll go over that in Creek. Now I'll send you guys some video links just to show you that you could automate this method of determining discharge cross sections. There are these remote controlled little boats that will navigate cross sections across the stream and get velocity at the depth. So one key streamflow concept is that if the channel cross section is not changing in time, discharge will always be the same at a particular stage. So this word stage might be a new term to some of you. Stage is defined as the elevation of the water surface relative to a datum. It's often different from the water depth because the datum that's used is one of the standard global datums that's used to determine, say, the elevation of mountains, elevation above sea level, and so on. And so if this is our datum where z equals 0 and z increases upward, maybe our stream bed is some distance above the datum. This is our water depth, which we might say is 2 feet. So 2 feet equals water depth. But maybe our datum is 8 feet below the bed of the stream. And so this 10-foot distance between the water surface and the datum would be what we call the stage. So stage is an elevation. So there's usually one value for discharge for one value of stage. There's a one-to-one relationship between stage and discharge. And the way we determine that relationship is through a rating curve. So a rating curve is just a plot of discharge versus stage. And one of the things you'll note is that this is on log-log graph paper, and it's very common that the relationship between discharge and stage fits a power law. And so if we look at these on linear axes, here's an example of a real weighting curve, and you can see this power law function that relates stage to discharge. You can download these from the USGS National Water Information Service. It's also worth noting that this relationship between stage and discharge may change over time if the cross-sectional area of the stream is changing over time as a result of erosion or fill. Stage is also something that we'll measure in the field. If you cross over a lot of bridges in this state, you'll see features that look like giant rulers that are stuck in the stream. These are called staff gauges. They're installed primarily by the USGS, but they provide a relatively easy way to measure stage. Remember, this isn't water depth, it's stage, so it's elevation above some datum, which might be an arbitrary datum. But what you'll see is that the numbers, they're usually in feet if they're at, if this is a USGS staff gauge, but every 1/10 of a foot is very easy to read so that you can read it from a bridge or from a distance. But if you want a more precise value of water depth, you have to look at the lines with smaller text. So again, we'll go over reading one of these in class. Then finally, at USGS gauging stations, which again are often located around bridges, there will be an instrument that can measure water depth in an automated fashion and record values of water depth continuously. I have one. This is a photograph of the type of pressure transducer that I have, and it's based on the fact that we can establish a relationship between hydrostatic pressure and the depth of water. Pressure transducers, however, will also be sensitive to dynamic pressure, or U squared over 2G. And so these pressure sensors are often deployed not in the stream itself, but in a reservoir that's connected to the stream, so that the water level within the reservoir is at the same level as within the stream, but there's no velocity, and so there's no dynamic head. So just to wrap this all up, we can measure water level continuously and relate it to stage. There is a linear relationship between stage and depth. It's a positive relationship, but it might not have an intercept of 0. We could relate stage to discharge using a rating curve. Remember, this is a power law function. This is stage. And in this way, we could get continuous estimates of discharge from gauging stations, and these are often available online, like at the USGS NWIS site. We develop these rating curves by measuring discharge at different points in time under different flow conditions, and the way in which scientists do this is exactly the same as what you'll be doing in Strawberry Creek. So hopefully this is a nice experience for you, and I look forward to the change of scenery and seeing you all in the field. Okay, bye.